Okay, this time I'm gonna record the story because I realized after your class and Ryan's excellent questions that that's really important. Um, I'm so tired over the pandemic summer that I forgot to tell the stories that I usually tell about the stuff that helped them make sense. Uh, so, but I remembered a good one for seventh and eighth. Let's say you're driving up to Lewis Cast to watch one of those games or competitions, and you're on the highway. Okay, you're riding with your friends. You skipped out on the physics test this Friday, so you're all pumped, and you're driving a little too fast, and the driver has to hit the brakes. What happens to everyone in the car when they hit the brakes? They they all lurch forward, right? Excellent. Okay, and the car, what happened to the car? In conventional words, you would kind of say it slows down. What do you think, Christine? Even if you don't come to a stop, in physics terms, what would we say? Oh, it's slowing down. But we didn't say slow down in our equations. That's right. We're accelerating, and we're accelerating backwards. So the car accelerates backwards, and you're part of the car. You're inside the car, and you lurch forward. Okay. And then the driver realizes, oh, okay, we can go fast again, but I'm showing off for my friends, so I'm going to stomp the gas. And the car accelerates forwards. What happens? Everyone in the car lurches backwards. Okay. So the lurch you feel is really because you're accelerating in the opposite direction. Well, okay, that ramp off the highway was not designed very well and you're taking it really fast because you forgot to slow down, the driver turns the car around a fast curve, and where does everyone lurch? Well, okay. Yes, their speed and momentum is going straight, but if you concentrate on the frame of the car, which you probably are inside with your friends, everyone seems to lean out, don't they? You go around the curve and everyone leans out. You have to, like, if you go really sharp, you have to like almost push yourself to stay straight up in the car, right? You can try it this weekend. You're probably going to drive somewhere, maybe just home from school. Okay, the school buses don't go fast enough to do this, but that's a good thing for them. Okay, but when you go around a curve, you feel the lurch outside, and if the acceleration is the opposite, that's right, you are accelerating inside towards the center of the curve. Okay, so you can feel this yourself. We must be accelerating towards the center. You just have to take it on faith, crunching numbers and making units match that it's v squared over r for now. I'm going to prove it on our first non-test day next week. It's going to be a headache. I didn't want to give you more headaches before the test. Okay, but I can prove it with geometry, that it's exactly v squared over r. Okay, so we sat through that little talk. I also have this device. I'm going to pause until I can video it for the people online. But you can try the riding in the car story yourself. More video. Have you ever been on one of these carnival rides? You walk in, it's like this room, we'll say 3 meters in radius, right? So it's like 20 feet across, this little circular room. You stand against the wall, or maybe you've seen video online, and it starts to rotate, and it goes faster and faster and faster, and you kind of slide up the wall, and then the floor drops out, and you can watch the ground racing by and hope it doesn't make you nauseous. Oh, man. Yeah, my daughter likes to take me on all of those. Make dad go. Anyway, so with a little quick force analysis, good warm up for your test, since this group's not taking it till Monday. Uh, what force do you suppose is pushing, providing this radial force? So I know if I move in a circle, just that fact, there must be the mass of the person, v squared over r, yeah, v squared over r, pointing towards the center. What force is that that's stopping them from going straight, that keeps them in the circular path? Sorry, I couldn't hear. This, the side of the wall? No. It's one of the ones we named before, all over the place in Chapter 4. Almost every problem has it. Close. Friction has a role here. Does friction, so there's a person against a vertical wall. Does friction push the person out from the wall? Oh no, that's right. Which one pushes up off the surface? Or which force stops them from smashing through the surface, which is what they would do? It's the normal force. So I have to show this example, or everyone gets stuck on the homework problems. It's actually the normal force that's pushing inward towards the center. You should go in a straight line once you get up to speed, right? Newtonian mechanics. But the wall is there and stops you from doing that and is actually pressing you towards the center. If you ever get a chance to go on this ride, you feel the pressure. And that's what people call the centrifugal force, right? Centrifugal means flee the center, and you certainly do feel pushed out against the wall, but nothing is going to move you out. You wouldn't fly away from the center if the wall wasn't there. You would go in a straight line tangent, perpendicular to the wall. But the wall is definitely smashing you in. Okay, and of course you have mg pointing down. So there is a role for friction. What must friction be doing? Sure. Friction is what's holding you up. If we had slick, icy walls, yeah, you would fall out. There would be nothing balancing gravity, and you would fall out. So friction is mu times the normal force. If you like capital N for normal force, you're looking smarter and smarter. Okay, because we got F's all over the place again. Okay, so it's the normal force that's mv squared over r, and the friction force that actually saves me. So to not fall, I need to have mg, the force of gravity, be less than or equal to the force of friction. Can I scroll down just a bit? No. Yes, I can. Everyone's written that down, I assume. Uh-oh. You need to write my question down? Oh, okay, those equations. Yeah, yeah, yeah. You need the equations. Okay, so mg has to be less than the force of friction, and the force of friction is equal to this mu times the normal force, always. Okay, we just had to figure out what the normal force is. Okay, in this case, it must be mv squared over r. So, whoop, I forgot my mu. I'm just ready to cancel that m. Mu mv squared over r, which is mu times the normal force. Okay. The masses cancel out. I have g times r. Okay. I'm solving for v. Taking the square root doesn't really affect the greater than less than sign. You could always, this is for homework purposes. You could always, and so I need the square root of this side. Ugh, that was a terrible drawing. Okay. Oh, and I gave numbers. What a goof. Okay. G is, of course, 10. R was 3. And mu was 0.5. Okay. So I need the square root of 60. I could have thought of nicer numbers for that. Okay. 7.75. It's not that bad. Meters per second. From meters per second to miles per hour, it's like 2.25 or something. So almost 20 miles an hour. And that's fairly realistic. You get going pretty fast. A little bit faster than you could run, probably. That's pushing them out. Okay. So that's complicated. Isaac Newton would say there's a fictitious force against the wall because you push on the wall and the wall pushes back on you. Okay, so there's an action-reaction force that we call centrifugal force. But it's really your momentum, which is a couple more chapters, trying to carry you in a straight line. You have inertia, and there's that Newton's first law is true, mostly, And so your tendency is to go really at constant speed in a straight line. And so to keep you on a circular path, that's the big deal, the wall has to actually smash you in. Okay, so that outward force, the pressure on you that you feel is actually your reaction force. You're just experiencing the normal force from the wall, and your body's reacting to it. You do feel smashed, and centrifuges do generate a lot of pressure. But you wouldn't, if the wall suddenly disappeared or you slipped out the top or bottom of the centrifuge, you wouldn't fly out. You would just go straight. So you can get in and get up to speed. Exactly. If only, that's right. There should be no force pointing out. Sorry, that is a big deal. Isaac Newton had to try to convince everyone. He wasn't very good at it. He's famously a jerk. Yeah. Okay, good. I know, if only we could do field trips to carnivals. I never have done that, and especially not this time, but maybe we can think of something. Okay.